Every challenge question then, part 30. This is the integration chapter, which is a really nice long chapter, which unfortunately has barely any challenge questions in it, which is sad because integration is fun. This obviously integrates to a log. It's 1 over a log of this thing here. Then you can put 11 and 5 in, which just make this. You can factorize out the 1 over a, and then 2 logs taking away means you divide the inputs to get this. Now that apparently needs to equal this, so therefore this input here, 11a plus b over 5a plus b, must equal 41 over 17, which means I think I can just set this thing here to equal that, and this thing here to equal that. And I've actually just been teaching quite a lot of simultaneous equations at school, so I think I can do this. Two pluses mean that you take away to get 6a is this, and then divide by 6. And then if you pick one of these two equations and put a is 4 in it, 4 times 5 is 20, take away 3 is 17, so therefore b is minus 17. How on earth do we find another solution to this, you ask? Because linear simultaneous equations only provide one pair of solutions. Where do we get the second from? Well, 41 over 17 could just be written like this, because that's totally the same thing. And then you can just say this is equal to 82 and this is equal to 34, and then do the same thing again, and you'll end up with your other two solutions. So that's great. 2 pairs. Fantastic. Next question. X equals k sine u. Differentiate both sides to get dx equals k cos u, because sine differentiates to cos, of course. At this point, you can square this thing here to end up with x squared equals k squared sine squared, and 9 minus x squared is just 9 minus k squared sine squared. Now, I realized here that I really want to factorize stuff out to get 1 minus sine squared, because 1 minus sine squared is cos squared, and then when I try and root this thing here, I'll just get cos, which might even cancel with this cos. That would be amazing, but I can only do that if this thing here is a 9, so therefore the substitution is going to be of the form k is 3, and I'll do the whole thing again, and I'll get this, which factorizes out. This turns into a cos squared. When you root it, you get a cos. You put it all in here, and this stuff cancels with this stuff. You end up with this, which is cosec squared of u. Now, off the top of my head, I actually don't know how to integrate this without t substitution, which I'm sure I'll cover when I get to FP1. But in any case, in the formula book, you have this fantastic little result here, where cot differentiates to minus cosec. So therefore, cosec integrates to minus cot. And that's great. Cot is cos over sine. And sine u is, of course, just x over k, or x over 3. And cos u is this thing over 3. So we get this. The 3's cancel, and you end up, I think, with exactly what they wanted us to get, which is fantastic. Next one, to find this area here, we're going to need to find this, this intersection here. So we can integrate up to there, and then integrate up the rest of it. So okay, let's set this equal to this. Sine 2x is 2 sine x cos x. I can divide both sides by cos x as long as I realize that cos x equals 0 might be a solution, which yields the solution pi over 2, of course, but pi over 2 is beyond the scope of this diagram, so that's kind of irrelevant. Divide both sides by 2, sine of x is pi over 6, which is in the scope of the diagram, so this must be pi over 6 here. So okay, the plan is to integrate cos x minus sine 2x to get up to pi over 6 to get this area, and then add in the integral from pi over 6 to pi over 4 of sine 2x minus cos x, because of course they flip over, so this one's on top this time, so that's cool. Let's do this. This integrates to minus sine, this integrates to a half cos 2x, with a plus, of course. Why is there a plus here? What have I done? Yeah, because of course sine integrates to minus cos. I'm just a moron. Yeah, cool. And cos integrates straight to sine. I just had that completely the wrong way around. Whatever. Cool. And then, of course, this one does the similar thing. We put the limits in. It's a good chance to practice your exact values. If you're going to university soon, you're going to need to know all these. It turns into all of this. And more quite good practice to cancel out all these fractions because they're not too hard to do. You eventually end up with something that ends up being like this, and you'll have your final answer. The last question is about integrating mod functions. Basically, there's one rule here, which usually is that you never integrate a mod function. You just draw a picture. This factorizes this, which means solutions 2 and minus 1. You draw a picture, and then you draw what the mod function looks like. This case, because it's mod of the whole thing, the negative parts have to flip over to be positive. And so mod f of x looks like this. And then the integral is just, well, it's the integral from 2 to 3, up to 3 here. The integral of 2 to 3 plus the integral from minus 1 to 2 of the function flipped over, which is just what happens when you times the entire function by minus 1, plus the integral from minus 1 to minus 3 of the regular function again. And I can just do this very slowly. I'll just integrate it all. I'll put everything in. I absolutely could not be bothered to do that without a calculator, so I just typed into calculator, and I got this, and that'll be my answer. The next one is actually even easier because f of mod x is just when you flip the graph in the y-axis. So this thing here goes over there, and you end up with this kind of picture. And now we can just integrate between 0 and 3 of the regular function and then double it, because this area, all of this area is going to be the same as this, so we can just double it. You do the integral, you put the numbers in, this one ends up being much easier, and you'll end up with your answer of -3. Thank you for watching, I'll see you next time.